All right, well, thanks for coming. It's really ridiculously early on a Sunday. I was thinking the only people who would be here are the people who didn't go to bed last night. So, thanks for that. I wish I was in bed. All right, so what about me? So I used to work at the NSA, do battery research startup. Hacked some phones, one phone down a few times, wrote some books. None of the books are actually here. And then I have some letters and stuff after my name. Oh, and best of all, there's an info.com about me. Well, I don't really get it though, so maybe someone can explain it to me. It doesn't seem funny, but it's about me. Okay, so anyway, as someone who like is always looking into something to work on and figure out how something works, I wanted to think of something to do that was sort of different, and I got inspired by seeing Barnaby Jack do his ATM talk last year at Black Hat. I was like, oh, this is really cool. This is something that's really easy to explain, right? It's it's hard to explain. Hey, I got a ASLR bypass or something. But it's pretty easy to explain. Hey, I can walk up to an ATM and I can make it give me money. And so I was like, well, I want a project like that. So I was like, well, it'd be pretty cool. So I saw this YouTube video where this idiot figures out how to light his computer on fire, right? And then the whole time when it's blowing up, you can hear him cheering in the background. So I was like, well, I want to do that. I want to figure out if remotely I can make the computer blow up. And that would be something I could easily explain to my grandma or something. It's like, I don't know if she would get why I did it. And a lot of times when I was talking to reporters, they're like, why did you do this? And I was like, I don't know, I just thought it would be cool. So the spoiler is I didn't actually, so this picture isn't mine. I didn't actually get fire or anything like that. And some of that is because I didn't, when push came to shove, I work out of my house, I kind of didn't really want to do that. And also, it might not even be possible, I don't know. But you can be the judge by the end of the talk of whether you think you can do it. Also, a lot of people got really upset because they're like, oh no, they're not going to let us take computers on airplanes, right? So no one will be responsible for that. But anyway, so check this talk out, and at the end you can decide whether you think it's possible. I'm not sure. That's basically the short answer. Okay, so I want to talk to you guys about smart battery systems, how they work. And then in particular, I'm going to look at the MacBook battery. These are the types of batteries that show up on every MacBook I've ever seen.
Come over here, because I'm
and then, any impact that this might have. So how do these things work? So it turns out there's a little chip on your battery. And this chip is part of the whole system of charging your battery. Is the one that's responsible for basically almost everything as far as how the charging goes. So this is the brains of the operation. If you read this from the specification document, it says, so the primary intelligence of the system is in the battery pack itself, and then further on you'll see it says so by relying on the battery's intelligence, they can safely charge and discharge. So the whole point in any chemistry, so the whole point is that the computer might not know what kind of battery is stuck into it, so it might not know how to charge it properly, but the battery knows how to charge it the best. So all the brains of knowing how much charge to give, how fast to give it, how slow to give it, when to stop charging, it has to be in the battery, because you could put one battery in that charges very fast and one battery in that charges very slow or something, and the computer won't know the difference. So this tells us that if we're interested in battery charging, you need to look at the chip on the battery. Okay, so I already mentioned there's a little embedded controller in there. And one of its main jobs is to make sure that nothing bad happens. And there's various things you can configure with, and on my MacBook Pro, I can pull up under System Profiler, you can get some information about your battery. And so here it says things like the device name, which is actually the name of the chip. This is something that on the MacBooks I was looking at, it didn't tell me, and there's a long story you'll see about how I had to figure that out. And then it has things like pack lock code, cycle count, which is how many times the thing is charged and discharged, how much voltage it has, stuff like that. And the way that the computer can figure this information out and display to you is it asks the battery, the chip on the battery says, hey, how much voltage you have, and the chip tells it. So there's a way to communicate back and forth between the computer and the chip on the battery. So what are some possible things you can imagine going wrong by attacking this chip? And again, one of the things I set out to do was to see if I could do this remotely. So everything I talk about here Like some of the times I'll show you things I do physically with the battery, but all the final like communications and all the attacks are things you could do just from the OS. So like you can imagine if you had remote access to the computer, you could do it. So what are things you could do? You could brick the battery, so make it to where it doesn't work anymore. You could remove all the safety features and in the worst case scenario have what the battery engineers call thermal runaway, and we call like explosions and fires and stuff. So you could imagine denial of service to the operating system. So if you had some code running on the battery chip that was constantly attacking the OS, that it'd be, the OS wouldn't work, it'd be slow or something, and then you would reinstall it, and that would still be the case, right? Because the problem wouldn't be with the OS, it would be with the chip. Again, maybe instead of just trying to deny service, you could actually figure out a bug in the part of the kernel that deals with the responses for the battery, because Apple's kernels are totally got no bugs, so that can happen. But so you can imagine a bug where the battery attacks the OS. And then finally, the battery's in sort of a trusted position, so it can sniff things like the BIOS starting up, or talking to the TPM chip or something. So you can imagine figuring out, you could just sniff the bus that pulled the battery and the TPM chip was on. So various different things you can do besides just blowing up the battery that's sort of interesting. Okay, so let's start at the beginning. So if you've known anything about like my career, it's like I don't do hardware really, I do software. So I find bugs and reverse binaries and stuff. And so I don't know why I decided to do this. I was like totally ill-equipped to do it, but you'll see, if you're a software guy who wants to learn about hardware, this is a good talk because you'll see all the stupid hoops I had to jump through. So I was like, okay, I have a battery, I have a computer, and now what, right? So of course I just said, well, let's just Google for it and see if it'll help me. So I Googled MacBook battery firmware, and then this like update thing comes up. So it turns out that over the course of maybe 4 years, Apple has updated the firmware on batteries 4 different times. And so I was like, okay, this is software, I understand this, let's get it. So I downloaded the updater and started reversing it. And so when you reverse it, you realize that it's basically just a bunch of function calls to this function IOConnect method structure is structure. And this function is what's used by applications to talk to drivers in OS X. So this is the way that you can tell a driver to do something. And the particular driver that you're talking to, or that this update is talking to, you can see is called Apple Smart Battery Manager. So that makes sense. So okay, now I'm starting to see, I've seen an application talk to a battery. This is good. I can figure out how this works. And then you start looking around more on the web, and you can find there's this open source package through Apple called Power Management. And this has a bunch of cool source code in it that sort of shows the code used by the updater a little bit. But they only give you, this is like typical Apple, they only give you some of the code, right? So you can't actually compile the thing. But I guess they've sort of fulfilled whatever obligation they had to release the code. But one of the good things is there's still a bunch of header files that are useful for us. So if you look at the header file, it actually says something like, it gives away some things about the specification that they're reading, which is the main one. So smart battery specification, and then it talks about some of the commands that it for sure knows about and whether they're read or write and stuff like that. So it's pretty cool. But it's not like you can just build the thing and use it. So you have to, the only way that I know to talk to the battery is you either have to write your own driver or you can communicate through the existing driver, which is what I ended up doing. Okay, so what does the updater do now that I know sort of how it talks? So and now I know what from the header file, the types of things that it's the language it's using. So it does things like it reads the device name off the battery and compares it to a list of device names that it wants to update. And then it checks like the firmware version and pack code and all these other things and compares it to see whether it's updated. And then it does some things that aren't in that header file, so I don't know what those are at the moment. And again, this is sort of a story of how I did it, so I actually know some of the answers now. And you'll know by the end, but let's just play along with it. You didn't know. And then I've seen some code that sort of sticks out to me, and I wasn't sure what it was. So it writes some word, like some 0414, I'm not sure what that is, and then 3672. So everything else was very sort of, read this, and then analyze it, read this, switch on it. And then all of a sudden there's this weird thing. So I was like, what's so special about these numbers? So again, I don't know how researchers work before Google, but that's what I always do. I just Google everything. So I Googled that number, and then I start to see things like this. So it says, if you look at some of these, it says, so here's one of them. So it says the default code, sealed, unsealed to full, blah, 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 blah. And then you see things like full access key security codes. And I was like, okay, this is sounding good. So if you download one of those documents, you'll see things like this. So it says unseal key, and then you'll see it's right here. So this is some sort of key that they're using to talk, to authenticate to the battery. And then there's this other key, full access key. That sounds even better, and it turns out it is. So the interesting thing besides this is I've also learned, because this document is talking about some Texas Instruments chip, that I know now that it's a Texas Instruments chip. So that's good. I know that they use this key straight from the factory. They didn't change it. So that's interesting. And then later on, I tried this other key for full access mode, and they didn't change that either. So I was able to, so now just by reading some document, I know how to unseal a battery, which I'll talk about in a minute. And then I know how to get full access to the battery, because Apple didn't actually change any of these values. So it's like, sort of a default password attack. So that was nice. And basically the whole talk revolves around this. So if they would have fixed this, then I couldn't have done anything beyond this, but they didn't, and so I get to do all sorts of fun stuff. All right, so I know the chip comes from Texas Instruments. I'm afraid to really look at hardware, so I got to figure out a way to figure out exactly which chip it is. So you can talk. I've already said you can talk to the battery. One of the things you can do is you can ask for different data for different what they call subclasses. So you're like, hey, give me subclass 1, give me subclass 2, and so on, and it returns some amount of data. And depending on which chip it is, it might, subclass 1 might mean something different to chip A than the chip B. And so by just querying for all the different subclass IDs and figuring out how much data it returns, you can kind of get a fingerprint for what kind of chip it is. And so the point is, I could have just ripped open the thing and seen what chip it was, but I really didn't want to do that. So it just shows how in one sense I'm really lazy, and in the other sense I'm the opposite of lazy. I'm willing to go through great lengths to avoid doing something. So for this particular battery that was on whatever MacBook I happen to be playing with at the moment, these are so for subclass 0, I got 22 bytes, and I got 25 bytes and 10 bytes. I started reading through all the different technical specifications on Texas Instruments site. And I finally found one that had basically these same links. So you can see things like first level safety. It returns 22. Oh, great. And then first level safety, that was first level safety voltage, first level safety current. You can see how much it returns, 25, and so on. So just by reading through this document, I get to see all the different links that things is returned. It exactly matches up with mine. So I figure out, hey, this must be a Texas Instruments BQ20Z80. And you'll see it is. So that was the way I did it, and it took like, a week or more maybe to write all the code and figure it out and read through all the specs and all that stuff. So here's a way you can do it in under 2 minutes. So you take a battery, right? Looks like this. There's little screws on the side. You unscrew them, rip off the plastic piece, and then you start to see this. So there's these lithium polymer cells. There's three, and then there's two rows of. So there's 6 of these guys. And then at the end, there's this little piece of plastic that holds a bunch of electronical stuff. So you start to rip that plastic case off, and then you start to see some chips. Right? I'm totally a hardcore hardware reverser, right? Chips and stuff. So then you can see inside. So then that unfolds, and then you can see basically everything. So there's a chip here, the biggest chip on this size, and you can read right on it if you get out like your magnifying glass. It says BQ29312. And so this is what it looks like if you look at it very closely. And I didn't do this because this is like a hardware thing. And Travis Goodspeed did this for me. And he's like such a hardcore guy that he found out I was talking about this at Black Hat. And just because he's just curious, he had a MacBook battery. He ripped it apart and he dipped it in acid and took this photo and all this stuff just because he was curious what it looked like. So this is what the chip looks like. And then on the other side, you see there's 2 more chips, BQ29412, and then the 20Z80, which we already knew about, and that's the big chip. And again, Travis ripped apart the chips and took some cool pictures and stuff. And all right, so then how else could I have figured it out? Well, it turned out in one of the header files I already had, I just hadn't, read them very closely. It says right here, BQ20Z90 version 110, and the other chip. So anyway, I could have done it even faster than ripping apart the battery. Oh well, live and learn. All right, so where are we at in the story? So I know what kind of chip is on the battery. I can get data sheets for it from Texas Instruments. I see how to talk to it with the driver, but I don't necessarily know exactly what to do, what to say, right? What's important to say. So then I had to figure out, how do smart batteries work, right? How does the whole thing fit together? So this is basically how it works. And again, there's this document called the Smart Battery Specification that if you're curious, you can read, and it'll tell you more about it. So there's basically 3 components. So there's the host, which is like the computer in this case. The smart battery, which is the BQ20Z80 and its associated chips. And then the charger. And the way these things work together. So the charger is the thing that decides how much, or the thing that sends the current to the battery. So the host does things like, so the battery can send out critical events to the other 2 guys, and it can also tell the charger how much to charge or how much to give it. So you can say like, I'm almost full, stop charging me, or it can say like, I'm almost empty, give me a lot of charge. And then it can tell the host like, hey, something terrible is going on, please report an error to the user or something. And then the host can say things like, hey, how much voltage do you have? I want to tell the user how much time they have before the battery runs out. So anyway, so this is the way that they talk. And the way they talk is on this SM bus. And the SM bus talks, the language they talk is I2C. And we'll talk more about all that stuff. Anyway, so this is basically how the smart battery works from a high level. And I have a white paper if you want to know more about it, but we don't have time to go into details. So I wrote, so talking to the driver is like kind of cumbersome. So I wrote an API that you can use, and you can download this. I have it available if you want to play with your battery. That makes it a little easier. So you can say things like read a word, the serial number. So this would return the serial number of the battery. You can unseal the battery. So I haven't really explained what that means yet, but now you can there's a command that will just do it for you. You can write a new manufacturer date, a new device name, and then this is the way that you read what they call data flash. So you tell it like, I want subclass ID 57, and then I read a block, and then full access, and then seal. So I just have this API that makes it easy to communicate with the battery. And one of the things that's sort of interesting about this is like when your battery starts to die and you take it into Apple to get it fixed, like to the Genius Bar or whatever, they can check the cycle count to see how old it is and whether it qualifies under warranty. And so now that you can do this with the API, you can just set it to something low, and then it'll always look like it qualifies. So if you ever need a new battery, download this tool, and you can go in and get a free one. Thanks for clapping when I tell you how to avoid your warranty. Okay, so what is the language that you can communicate to the battery with? And so it's called SPS. And so there's these big lists of standard SPS commands you can send. Then there's these extended ones that are a little more dangerous. And then there's the data flash. So there's a document that is for the BQ20Z80, BQ29312A, and that's exactly what we have. So it says exactly what each command means and what to expect from it. So there's lots of stuff you can do. Lots of parameters you can change on the battery. So things like design capacity, so how much you think, or how much it can hold, how much voltage it can hold, what kind of chemistry it has, thresholds to where it thinks it's got too much voltage or too much temperature. And then there's these second level thresholds, which these other chips I haven't really talked about are in charge of monitoring, but you can set these thresholds too. And then there's things like built-in model. So impedance is some electrical term, but what? So anyway, but what they mean is Texas Instruments, the way they figure out how much charge is left is something they call the impedance track algorithm. And it's the way that based on how much charge they've seen leave, they can estimate how much charge is left. Anyway, so they have this table that helps them figure that out. And then they have also a table that figures out what the temperature is and all this stuff. So anyway, there's lots of data you can mess with, basically. So I mess with it, right? So the first thing I do is I take all those thresholds and I like boost them way up because I don't want it to ever stop charging, right? But what happens is not interesting at all. What happens is it still just charges right to where it's full and stops. So those parameters I've been messing with are things like, well, when things go wrong, then when they hit this level, then we turn ourselves off, right? But things didn't go wrong. Things went just as perfect as ever. So I need to figure out a way to mess with it at a lower level. And so the lower levels are exactly this unseal full access and then what's called boot arm mode. So let's talk a little bit about that. So there's 4 modes that a battery can have or can be in. And when it comes in your computer right now, like, hopefully everyone who's got a computer here right now, their batteries are in sealed mode. So let's talk about that first. So this is the way, like, Texas Instruments, has these chips. They're from the factory. They seal them up. They send them to Apple, who puts them in their batteries and send them to you. And presumably they don't want you messing with your battery because it could be dangerous. And you can't really do any harm to your battery when it's in sealed mode. So when it's in sealed mode, you can only run a list of extended SPS commands, and they're read-only access at that point. So you can ask the battery things like how much voltage you have, but you can't tell it anything. So there's not much harm you can do at this point. And then there's the unsealed key. So that's the 327 or whatever thing I pointed out. So when you unseal it, you get a little more access. So this is sort of like going from user level access to root access or something. So now you can access the whole data flash space. You can do some of the extended commands, and then some of the regular commands are now read-write. And as I mentioned earlier, the way I figured this out, of course, was that the updates, the Apple updates, you enter this mode. This is the mode they enter. They don't ever go any higher than this. So beyond this, again, they use the default key, FFFFF. And if you enter that, you can enter full access mode. So here, basically, you have the whole run of the device. This is probably more like the administrator account. Or it's really almost equivalent to like loading a driver or something. So you have every SBS command. Every command is read-write. You can enter these other even more special modes. And like I said, so Apple, in none of their firmware updates did they ever have to even go this far. They couldn't do the changes they needed to do at the lower level. These other 2 modes you can enter, one is called configuration mode. And what this is something that really only like an engineer at the factory would ever have to enter. And it's a way to just configure the device to how things go. So like you know exactly, you're charging it, you know exactly how much current you're giving it, and then you tell the device, hey, I'm giving you this much current. Make sure you configure your little internal state to know that that's exactly what you're getting. And so here's a way that you could do that if you felt like doing that. And so you can imagine screwing up your battery quite a bit by telling it the wrong things here, right? So you tell it like, hey, I'm giving you like almost no current right now, but you're really giving it a ton of current, right? And then its internal state's gonna be like, okay, whenever I see, this, I know I'm not getting very much or something. So anyway, you could totally screw up your battery probably doing this, but I didn't mess with this. And then I was like, well, so I got this from a document, and the document said the only things you can configure, or the only things they used in the example that you could configure was current, voltage, and temperature. And I was like, I wonder if there's other things you can do. And I didn't know, because like, why choose the numbers 60, 63, 61, 62, right? Does 59 work? I don't know. And since I don't know much about hardware, so the first thing I did was I went to the Texas Instruments site and I just asked somebody. So they have this like nice little forum and stuff. And so I said, hi, is there anything you can do besides current, temperature, voltage? And this very nice employee named Jackie responded. And she says, oh, no, that's all you can do. And, this is a very nice interaction. I'm very happy, and I feel like I'm part of the Texas Instruments community, right? And even better, look what it says about me. It says I'm a prodigy. So, I'm just feeling really happy and really good, and I love Texas Instruments at this point. So you'll see later, the story changes about my feelings for Texas Instruments. Okay, so the final mode, and sort of the most powerful mode, is what they call boot round mode. So this allows low-level access to the device, so direct access to the flash instructions and the firmware. And there's no documentation in the document I have at this point that talks about how to do it. So I have to figure out how it works. So I have to go buy some more hardware. So Texas Instruments has this evaluation kit. So it comes with like all the chips that are on your battery, and like this USB thing and software, and it's all sort of nice. So this is what it looked like in my house for a long time. So batteries and chips and wires laying around. And then you can see my little measuring device I went down to Radio Shack to get. And growing up in the 80s, I thought the guys at Radio Shack are really smart, right? So I would go down there and I would ask them these questions about batteries and how they charge, and they'd be like, why do you want to know that? I was like, well, I'm doing some research or something. I don't know. So I would just make it up. But anyway, it turns out they don't know jack shit about this stuff. And then so they actually said, well, there's a store down the street called Battery Plus. Why don't you go there? They know about batteries. I was like, great idea. So I went down there, and they know even less. They're like, well, I have a charger for your cell phone. I was like, just forget it. So anyway, so I had to figure out everything on my own. The Radio Shack guys aren't as smart as I thought they were. Okay, so this is what the software looks like. This is the guy from my title slide. So they have this funny little battery dude who is like their version of Clippy, and it's sort of funny. So you get the software running, and you can talk to the battery by changing parameters here, and it explains what everything is. And these are like bit fields. It's like a pretty cool little program. The really bad thing is it runs on Windows, so I couldn't reverse it to figure out exactly. Well, I couldn't just use it to talk to the battery that's on my actual computer while it's running, right? I can only talk to the evaluation kit. Here's what the data flash things look like. But of course, the button that really interests me on the side, so there's SBS data flash, is the one that's called Pro, because that's where all the good stuff's going to be. So it says right here, this screen is only for advanced users, and I'm clearly an advanced user. I'm a prodigy. So some of the things you can do is you can send. So it says read words, and you can, these are low-level boot ROM commands you can talk about. And then the really cool thing is you can actually flash it with a new firmware. So then my plan was, okay, well, I'll figure out what all those different things look like over USB, and then I'll flash it, and I'll sort of spy on it and see how it flashes it, and then I'll flash it with whatever I want. But to do that, I need to sniff what's going on between this Windows program and the evaluation kit. So I looked at one of these files that this program takes, and then it uses it to flash the firmware. And they're called SENC files. And so you do a little research online, and SENC stands for encrypted SREC. And so I was like, well, I guess I got to reverse the encryption. So I did. It turns out it's like XOR. So, and to be fair, it's not XOR with just 1 byte, because that would be trivial. It's like XOR with 2 bytes. So it's better than what they could have done. It's probably version 2. So anyway, if you tear apart what these SREC files look like, there's some header stuff. Then you get the entire data flash, all the instructions, and then some checksums and stuff. So that's what these files that you load into the program look like. So I wrote a PyDebug script, which basically intercepted all the data going over USB and logged it. So then I could do things like do a raw read and see what it looks like, do a raw write, see what it looks like, and then I could do an entire flash of the firmware, and then I could compare and figure out what they were reading, what they were writing, what values there were, and stuff like that. So I could figure out how it was flashing the firmware. And so by sniffing, I saw that, okay, to read, it sends this byte 8, to write, it sends this byte 4, and so on. So then I went back to Google, and I Google SMBus boot ROM, read 8, write 4, and then this document comes up that tells me exactly how to do it. So Google again for the win. And the other thing that's great about this document I found is it lays out exactly how the firmware is structured. So now I know what's going on. I sniff the programming of a SENC file, and it does this. So it erases everything, programs 38 rows of data flash and 300 rows of instruction flash. So this is the whole thing. If I can do this, then I can reprogram the chip to do whatever I want. So I'm getting close. So where am I at now? Well, I know how to write things in boot ROM mode. By looking, I can probably figure out how to read things, so I could probably dump the firmware, although I haven't at this point. I can get the data flash, even stuff I couldn't have gotten before. And the problem is I can dump the data, I can dump the instructions, right? I can dump the firmware, but I don't know how to interpret. It's just a bunch of data at this point. So what I really want to know, so I do that, I dump it. And what I really want to know is how to disassemble it, right? So I need to know what kind of chip it is, right, so that I can load it in IDAPRO and tell it. So again, I go back and I'm like, okay, let's see if Jackie can help me. She was really nice last time. And again, like I'm always like super nice and friendly because I want to, be that kind of person, right? So I'm like, hey everyone, what kind of chip is on this? Is it like, some PowerPC thing or something? Thank you. And then this other guy who's a real asshole writes back, proprietary. That's all he says. One word. Like, is that even a sentence? Does that need a period? So anyway, this guy is not Jackie, right? He's not as friendly. So the way you treat people like that is you just kill them with kindness. So I'm like, oh, thank you for your great response, which of course wasn't a great response. So I'm like, do you mean like it's proprietary in the sense you're not going to tell me, or it's proprietary in the sense that like there's just no documentation and it wouldn't help me? And he's like, oh no, it's the first case. Some key customers, probably Apple, they want to write their own, and so we don't tell anyone about it to protect their intellectual property. Sorry, right? So he at least was a little more friendly, but he wouldn't tell me anything. So I was like, well, I guess I'll just have to steal their intellectual property. So I'm like, okay, I'll just pull it up in a hex editor, and actually at first I just said, okay, well, I'm screwed, and for like 2 weeks I did nothing. But then eventually, when I couldn't figure out anything better to do, I was like, well, I guess I'll just try to figure it out. So I pulled it up in a hex editor, and it's just a bunch of binary stuff, not surprising. But the one thing you do notice is there's these threes, right? Like, what's up with these threes? And there's more threes, and they're sort of evenly spaced around, right? So I was like, well, that's something, right? So you notice that the threes are all spaced every third character, right? So I was like, well, maybe there's some alignment stuff going on. So I'm like, maybe it's 3 byte aligned, right? And then when you align it by 3 bytes, you notice the next thing, which is the third byte, the high nibble, is always 0, 1, 2, or 3. So, okay, that's interesting, right? I'm making some progress. And so I'm like, well, maybe these are, every instruction is then 22 bits. That would make sense. And the good thing is, how many chips out there could possibly have 22-bit instructions, right? This has got to be pretty rare, so maybe I can actually find it. So then the other thing I looked at was the end of the firmware, right? Because there's something sort of distinctive at the end of the firmware, is there's this 23FFFF, and then there's like a ton of these 3FFFFs. It's like, what's up with this, right? So then I started thinking, so if I had firmware, if I was writing firmware and I had a certain amount of space and my firmware wasn't quite big enough to fill that whole space, what would I put at the end of the firmware? Any ideas? So they have to be instructions, no ops. So I'm like, well, maybe the 3Fs are no ops. And then what about so then right before the no, so the very last instruction that's not a no op, what instruction do you think that might be?
Jump back to itself.
Maybe. It's not, sorry. Good try though. Anyone else? Exit? So that would have to be like a system call or something, but it's not. Any other ideas? It's fun to know the answer, no one else. What's that?
It's proprietary.
It could be proprietary. I'm sure that's what Doug would say, because he's an asshole. So how about this? So the end of the code, say it's a function, right? There's a function at the end. Like, what do you think the last instruction of a function might be? Return. Okay, so yeah, so I think, so my theory at this point is 2, 3 FFFF is a return, and 3 FFFFF is no op. Nope, there's more. So I searched for more 23 FFFFs, and they're sort of spread throughout the file, and and there's a bunch of them. There's 410. So this is really looking like a return instruction. So at this point, I was sort of still like, okay, so now I can't disassemble the whole thing, but I can disassemble 2 instructions anywhere they show up in the file. So it's still not making that much progress. But my coworker at the time, DM Lozakis, he's like, well, he came up with this Google command. His Google foo is much stronger than mine. So he Googles for these, and what does he find? He finds exactly the document. So it says things like 3FFF no op, and then you get things like 23FFF return and stuff like that. So you download that document, and then it tells you what kind of chip set that is. It's called a CoolRISC C816, and you can download that text sheet, and it says exactly what chip it is and how to disassemble things on it. So this is perfect. And so this is basically what Doug wouldn't tell me. So anyway, there's so how does this chip work? It's 8-bit, It's Harvard RISC-like, so that means there's instructions and there's data, and they're not mixed together. It tells me how big the data flash is, so this is like, you know, where it writes data, 64K. And the instructions are 64K 22-bit instructions. 8-bit registers, nothing in IDA Pro for it to help you disassemble it. So, you know, I tried every single one. There's like 30 chips, so I just try this chip, try this chip, try this chip. No luck. So then I decided, well, I'm going to have to write my own IDA Pro script to disassemble this for me. So here's more like on the registers. So registers are 8 bits, but sometimes they combine them to make a register that's like 16 bits. And these are all the instructions it can do. So the good thing about writing your own IDA Pro disassembler is if it's RISC, there's not that many instructions you have to implement. So that was good. And then, so there's this data sheet that says when you see these bits, it's this instruction. So you basically just have to translate this into Python and load it in IDA Pro, and you're good to go. So it's sort of a, you know, a labor of love at this point, but it's not that hard. And then finally, I can dump one of these firmwares into IDA Pro, and it'll actually disassemble it for me. So you have to do some things to make a data section and an instructions section, but once you do that, it loads. So I loaded it, and anyone who plays with IDA Pro knows that this like ugly brown color is bad when you disassemble things. So I did it, and it didn't really disassemble a whole lot. But I know the fact that you know, there's all the instructions are 22 bits, and they're 3-byte line. So I wrote a script to go through, and every 3 bytes just, you know, this is code, this is code, this is code, this is code. And then things are much better. So I disassembled the whole thing, and then I can start to analyze it. And you can look through the code, and you know, the thing I understand is how to talk to the battery, so I can see things like when an SPS command comes into the battery, how it handles it. So like these, if you see, this one was for, if you ask for the device name, it does this. If you ask for the manufacturer name, it does this and stuff. So now I can see the firmware on the chip, disassemble it, understand what it's doing. And I can, in theory, I could flash a new one that did something different. So then I start to do that, right? I'm like, oh, this is great. I'm going to flash a new one that does really bad things. So I can dump and disassemble. I can look at the data flash, even parts I couldn't get to before. The problem was I would take a dump. So I would take a dump of the firmware. I did that too. Take a dump of the firmware twice in a row, and I wouldn't get the same thing. I was like, well, that's weird. I was like, oh, well, I'll still try to flash it. And then when I do that, I would just totally brick the device. So I got into the habit of buying new batteries a lot. So these batteries are 130 bucks through Apple. And I was just ordering like 2 or 3 of them at a time. So it got to be expensive. And here's all the batteries. It's not even all the batteries I've bricked, but a pile of batteries that no longer work. So while I like humiliate Apple sometimes by talking about how you can just mess with their batteries, like I gave them a lot of money, so it's probably like, it was pretty much an even trade probably by the end. So I was like, well, I know, you can buy these like cheapo batteries from China. I'll just buy those and it'll be cheaper. So I bought this one, it was only 43 bucks on eBay. But they actually changed the unseal password, so I couldn't mess with it. So I couldn't use those anymore. So that's the only battery in my house I think that works because I couldn't mess with it. So eventually, after bricking all those batteries and I couldn't figure out what was going on, I finally did figure out what was going on. And it was that when you do these boot ROM reads, they're not always dependable. So sometimes they just return random stuff. And so I just changed my API to, it reads it a few times and verifies that it's the same thing every time before it accepts it. So once I implemented that fix, I'd only destroyed like 6 batteries. Then if I dump the firmware more than once, I get the same thing. So this is better. Okay, so then what's the next problem I run into? The next problem, and if you do this stuff I'm doing, you get this a lot on your computer. There's X. This is bad. This means there's something wrong with your battery. So I would patch the firmware, and then I would get the little X, and I was like, oh, this is a drag, because I used to be when I got the X, I had bricked it. So this time it's not bricked, it's just unhappy. So I looked and I saw that what it's doing is it's querying this PF status SPS command, and it sees that there's this bit set called data flash failure, and that's why it knows that something's wrong, and that's why it gives you the big X and it won't charge anymore. So on the data sheet you can read what data flash failure means, And one of the things is instruction flash checksum does not verify. I was like, oh man. So I change it. There's some checksum, and I don't know what the checksum is. I don't know how to fix it, and so again, I'm sort of back into misery. So, but now the good thing is I have the actual firmware. I can disassemble it, and I can see how the checksum works. And so there's some code in ROM on the chip that the firmware talks to, but you can't actually change. And one of these, and this is documented in one of those documents I found, and one of the functions you can call is to compute the checksum. And so I saw exactly where that function was. I looked at what functions call that function, and there was only two that call it. So one is if you send in an SPS command, manufacturer access with subcommand 22, which doesn't work for me, but I saw on the internet someone talking about that's supposed to give you the checksum. So I was like, okay, I'm on the right track. And then there's some other function that calls it too. And that other function is the one that we care about. So if you reverse that other function, it looks like this. And this is for, they switched this function for older firmwares versus newer firmwares. So let's look at the older one first. So what it does is it computes this address, 4214, which is somewhere in data flash. It loads it into this register, the value there, so 4 bytes. And then it compares it to 0. So and then if it's 0, it just goes down to the bottom of the function. And if it's not 0, then it calls it has the the firmware compute the checksum. And then it starts to compare the thing that the computed checksum with the stored checksum 1 byte at a time, right? And if it disagrees, then bad things happen, and if it agrees, good things happen. And so the thing that's really funny is if the stored checksum is 0, it doesn't check at all. So it's like some sort of debug mode or something. So all I have to do is set a 0 into the stored checksum, and then I never have to worry about checksums anymore, which is exactly what I want to do. The newer firmwares are a little different. So I guess they found out through some trial and error or something that sometimes you just end up with 4 bytes of 0 randomly, and then the checksum doesn't check, and something bad happens. So they built in this little decoder. So it's like encrypted or decoded or whatever they want to call it to the checksum. So now instead of 0, they take this stored checksum, they do this little algorithm on it, and then they compare that. And so instead of storing a 0 anymore, you have to store a decoded 0 or an encoded 0, I guess. So it's still just as easy to turn off. So for the older firmwares, you just store a 0 in data flash in the right spot. For newer ones, you store an encoded 0, which turns out to be this, 0, 3F, F7FF. Or there's actually a flag that turns off the checksum, it looks like too, but I never actually did that, so I don't know if that works. So the bad thing is, you have to, in order to set this in the data flash, you have to go into boot ROM mode. And from experience in that pile of dead batteries, I don't like to do that if I can help it. So I figured out a way to do that without going into boot ROM mode. The way you do that is, there's these SPS commands that allow you to read various things, like various subclass IDs, remember that, from the data flash. But they're not like in order in the data flash, they're just sort of random spots from the data flash. But since I have the real data flash and I can do each SPS command, I can kind of figure out which SPS commands give you which parts of the data flash. And it turns out that one of them, 57, which is one of the ones that's not actually documented, in the middle there is the checksum. So now instead of going into boot ROM mode, I can just set that, I can just use the SPS commands to set that save checksum to the value that makes it turn off. And so this is the code that actually does that. So I read it in, I set it, and then I write it to the battery. Okay, so now where am I? I have a function and the API that will let you patch the firmware to whatever you want. And here's how it works. You give it an offset, you give it what bytes, how long it is, and whether you want it to actually do it, and then you can see that it actually works. So I can, so where am I at? I can make changes to the battery through the SPS commands, through parameters. I can actually flash it with any firmware I want. The thing I don't understand exactly is how the whole charging thing works, right? So if I understood that, I can make the firmware do what I want, and what I want it to do is to just charge a lot and not ever stop. So to understand that, I had to actually figure out how the interaction works a little bit, and so I had to sniff the traffic going from the charger to the chip on the battery. And so first I need to figure out like how the hell this works. You look at the battery, there's these 6 little things it could be. And so I just ran a bunch of wires between the 6 and I figured I would sniff it. And obviously I'm not a hardware guy here. And this was a really bad thing because somewhere when I was making this great little wire mess, I must have shorted out something because all of a sudden my computer wouldn't work anymore. And so I took it into the Apple store. And they're like, oh, your logic board is fried. And they're like, what happened? I was like, I don't know. I just wouldn't turn on one day. I wasn't doing anything. And so they gave me a new one. It's really, really nice of them. So yeah, the Genius Bar is really good. Yeah, well, they're just as dumb, but they give me stuff. So sorry if anyone here is a Genius Bar. Okay, so then I was like, okay, well, clearly just clipping things wildly onto my battery is not a good idea. So I'm going to build my own wire, and I'm going to get, I went to Radio Shack and got a solder gun. It was great. This didn't work. So the actual way, if you want to get to the internal components of it while it's running, is it turns out you can just like take the keyboard off, and then you can see where the battery is running. And so then you just plug in all your little probes, and then you're good to go. This is the professional setup. It only took me a logic board and a bunch of wires and a week of my time to figure it out. So you do this, you hook it up into a logic analyzer, and you can see exactly which channels are the ones that talk on the SM bus. Okay, and then you can actually see the traffic that we're talking about, right? So you can see on this one, it's writing to 8, SPS command 8, which is temperature, and it's reading the response, which turns out to be 67.9 degrees. Makes sense. Then the next one, it's writing 14, which is charging current, and it's getting the response 3400. So now I can actually spy on it while it's talking, figure out exactly how the charger figures out how much charge to send, because I want it to send a lot. So I got another piece of hardware called a Beagle, and this thing will record for a long time. So you can see it, it's writing 16, reading something, writing 8, reading something, writing 14, reading something. And I can just let this run for hours to make sure that there's nothing weird going on. And so that's what I did. So I recorded all the traffic for an hour while the computer was turned off, so the host is off. All that is the charger talking to the battery, and the battery talking to the charger, of course. And the only things I saw in that whole hour were queries for these values. This is all that happens between the charger and the battery. So it wants to know the status, the temperature, the charging current, stuff like that. And most of these things don't even change. So like your battery status doesn't really change. The temperature changes just a little bit. And like things like your mode doesn't change. So of the things that change, there's only 5 things, right? So if I can manipulate those 5 things, I can completely confuse the charger onto what the status of the real battery is. And of those, really only 2 change significantly. Okay, so that's basically where I am. So what can I do at this point? Well, I can certainly brick the battery because I did that to myself lots of times. I can change what the charger sees when the battery talks to it. And then I can imagine putting code onto the battery to attack the OS. So how do you brick it? Well, that's super easy. And here's a way you can do it with my API that I provided. So all you got to do is go into full access mode. Thanks, Apple, for that. And then you can go into boot ROM mode, which is the really bad one. Then you can erase data flash, and then you just go back to try to execute that erase thing, and the battery is dead. How do you make firmware changes? Well, we've seen how to do that. So what particularly do I want to do? Well, you can take things like relative charge, full charge capacity, voltage, things like that. And when the charger asks the battery how much it has, you just lie. So how do you do something like this? Well, it turns out the SPS commands you care about are between 3 and 16, and there's one function in the firmware that deals with that. And it looks like this. It's just a big switch statement on what the SPS command you asked for, and then it does something different each time. So I went in and I patched the firmware to do something different. So when you ask for SPS command F, which is remaining capacity, which is like how much charge do you have left, instead of returning the remaining capacity, it returns a manufacture date. And then when you ask for full charge capacity, it returns a serial number. And the reason I chose those 2 things are these are read-write words that no one else cares about. So I can set them to whatever I want. And the charger's not going to care that the manufacturer date's changed, but all of a sudden it's going to think the remaining capacity is something that's not the truth anymore. So this is what the code looks like before. So this is for cases F and 10, which were remaining capacity and full charge capacity. This is the way it used to compute it, by talking to the hardware and figuring out what it really is. Now what it does when I patch it is it just jumps, it adds to the SBS command, and then it jumps over to the code that handles that SBS command. So it's pretty simple. And now when you ask the battery what its remaining capacity is, it coincidentally is exactly the same as the manufacture date. And likewise, full charge capacity is exactly the same as the serial number. Okay, so now I re-sniffed the whole thing, and I can see that it's true, just by watching the sniffing, that it's now lying to the charger. So I can set these even live while it's running to arbitrary values. I can see that the amount of charge that the charger is giving does change, but it's not like a real simple algorithm. So it's just because the serial number is not going to change, and so the charger is like, hey, how much charge you need, and the battery says how much, and it keeps asking it, and that never changes anymore, right? And so I was hoping that would mean that it would just keep charging it at the same rate, but it's smart, and it figures out like, hey, I think there's something wrong with this battery, and so it starts to still stop charging at some point. Anyway, you can imagine, this is basically where I stopped. But you can imagine making it smarter, where it slowly tapers off what it needs, but at a different rate than what it really should be tapering off. But anyway, you can imagine messing with it more. And then there's one other piece that might ruin your fun if you're trying to blow up a battery. And there's these thermal cutoffs. And it's these little tiny cutoffs that when a certain temperature is reached, they just, there's some chemistry happens, and it just breaks the circuit to where you can't charge the battery anymore. So it's possible that this is just the first layer of defense, and these guys are smart. They don't want batteries blowing up. So this is another layer of defense you would have to get around if you want to blow up a battery. Oh, and then one of the reasons why that battery, even though they were smart enough to change the unsealed password, they didn't actually include one of these thermal cutoffs. So this is why you probably shouldn't buy the $40 batteries from China. All right, so what else could you do? So you could potentially write an exploit that launches from the battery to the kernel, because if I was writing the kernel and I was the one responsible for reading in values from the battery, I probably wouldn't think that the battery was going to send something bad. So it's probably not superly well defensively coded. The funny thing was, Apple called me. I'll be done in like 1 minute. So Apple called me and were like, hey, we really don't think you should talk about this stuff. And I was like, yeah, no, you don't think that. And then they said we really don't like how you talk about how the battery could attack the OS, because we don't think there's that much code in the kernel that you could talk to, and so we don't think there's any bugs there. And I said to them, like, well, if I always thought that there weren't any bugs in code because you told me I would be out of the job. So I still think you could do it. All right, so then you could find bugs by fuzzing it. Yeah, so you could fuzz the kernel from the battery. It'd be kind of fun. And if you're scared that someone is going to do something bad to you, and there's someone was actually at the conference here was telling me that they have this weird battery that acts strangely to their OS or something, so it's possible. So I have this program called Gun that basically seals up your battery chip so that you can't unseal it anymore. And this is the code that does that. Thanks to all these people who helped me out, and that's it. So you can download the white paper, tools, all that stuff if you want to play with it yourself. Thanks. I don't think we have time for any questions. If you just grab me out in the hall if you have questions. Thanks.